Hello and welcome to Curiosity Cake. I'm your host, Lee Delaney. On this episode, I'm talking to Dr. Claire Lee and asking her what the universe is made of. Claire is a particle physicist and is currently working on the ProtoDUNE Single Phase Detector at CERN for Fermilab. Previously, she has conducted research at the ATLAS experiment at the Large Hadron Collider at CERN. Don't worry if that doesn't mean much to you right now. Claire does a fantastic job of making all of this complex physics much easier to understand, but essentially we're talking about the smallest building blocks that everything is made of. As always, hit the subscribe button, rate and review on Apple Podcasts, Podchaser and Good Pods, and follow me on Twitter and Instagram via the link tree in the notes. Now get yourself a cup of tea, grab a fork and dig into a slice of Curiosity Cake. Curiosity Cake. So Claire, welcome to Curiosity Cake. Thanks for giving me your time.
Thanks very much, Lee. It's really exciting to be here.
This is one of the topics that has really fascinated me for a really long time. And the actual role that you have, the job that you have, the work that you do is something to me that seems like it's one of those very glamorous kind of science roles, but it's one of those things when I think about, if I was a scientist, that's what I'd really want to do, because you're kind of answering really the most fundamental kind of questions of like what is the universe made of. So can you maybe just tell us a bit about yourself and what you're doing, really?
Sure. Okay, so my name's Claire. I am a South African particle physicist. I did my schooling and all my university in South Africa. So I was lucky enough, though, when I was doing my PhD to get a joint position to be based at CERN. So that was pretty exciting. It's obviously really, really exciting and really great to be at the place where the experiment is that you're working on. Mm-hmm. So I was able to move over to CERN with my partner and our 1-year-old kid, which was terrifying. Moving to a country where we didn't speak the language, and yeah, we visited a few times. I'd been to CERN a couple of times, but moving to a different country is another thing entirely. But it was really, really great, because CERN is it's like no other place in the universe. You are probing the secrets of the universe, and then you are hanging out, eating your lunch in the cafeteria, and a Nobel Prize winner walks by, and then you're having discussions with your friends about everything from physics to where the best skiing is this weekend. So yeah, it was an amazing experience, and we've also been lucky enough to stay here since I finished my PhD. So after my PhD, I then did a postdoc with Brookhaven National Laboratory. And I should say that I was working on the ATLAS experiment at the LHC for all of that. And then just this year, I moved to work for a different lab in the US called Fermilab. And with that move, I also changed experiments. So now I'm working on a neutrino experiment called DUNE. And we have prototype detectors for DUNE here at CERN called the ProtoDUNEs. So that's been another great change in my life. And learning about a whole new different type of area of particle physics this year has also been really cool.
Awesome. And there's some good acronyms in there, but just LHC is Large Hadron Collider.
Yes, so the LHC is the Large Hadron Collider. That is the world's biggest particle accelerator. We're offline for maintenance at the moment, but they'll be starting up again towards the end of this year or end of next year or something. No, end of this year, beginning of next year. And they take the LHC, the Large Hadron Collider, takes protons and speeds them up to very, very close to the speed of light. And once they're going this fast, they smash them together. And the point of that is to see whatever comes out.
That's very scientifically put.
Basically, that's what we do. And then ATLAS, it's another acronym. It stands for toroidal LHC apparatus, but nobody really cares about that. But anyway, Atlas is one of the experiments at the Large Hadron Collider. So its job is to detect anything that comes out of these proton-proton collisions and see what those are and use that to infer what happened during that collision. And then, that can tell us a little bit more about how the universe works.
Mm-hmm. Brilliant. And just a bit of a silly question, what do Nobel Prize winners eat for lunch?
Probably they're probably quite healthy and eat vegetables and stuff. Although they do make really nice pizzas in the CERN cafeteria. And a few years ago, they had Higgs boson pizza day, so that was quite fun. And then they had pizzas with different ingredients, making pictures of Higgs collisions and stuff. So I mean, if I was a Nobel Prize winner, I'd totally eat Higgs boson pizza.
Brilliant. So we'll get
and lots of coffee.
We'll get into all the detail of what the universe is made of. That very simple question.
Yeah, awesome, simple one.
But I'm curious for like ordinary people on the street. We can go about our everyday lives, do all the things we need to do, without really having to know what the universe is made of. So why is it something that we put so much kind of resource and effort into, and that you're obviously spending your life doing?
Oh, that is a question. Right. Okay. So I think that there's different reasons why as individuals we go into science. Personally, I always really enjoyed thinking about things and figuring stuff out and wondering about what it is that the universe is made of. But I think in general, it's actually a very fundamentally human thing to want to explore and to want to push these boundaries. I think asking the question of why do we want to figure out the basic particles of the universe is very similar to asking a question like, why should people climb Mount Everest? Or why should people free dive hundreds of meters down just to see if they can, or to see what's there? I think there's some part of us as human beings that drives us to want to explore and want to push boundaries and want to see how far we can take ourselves. And I think that this is just that particle physics and science in general and everything like that is just another facet of that basic humanity that we have. So I would argue that, doing this type of fundamental research is absolutely important for humanity, because it not only do we discover things about the universe and therefore probably get a lot of technological advances as well, but I would also argue that it is something that actually keeps us human.
That's a brilliant answer.
Thank you.
I think it's very well put. So let's get into all the detail then. So we've both mentioned particles a few times there. So what are particles?
Cool. Okay. So when I say particle, I am talking about something that is the smallest possible thing that you can use to build up the universe that we see around us. You can think of it as like the basic puzzle pieces, or just the basic pieces that are needed to create stuff. In fact, actually, most sciences deal with this type of way of thinking about things. So, for example, if you are a medical doctor or a surgeon or something, you think about the pieces of the human body, like you could think about the organs inside as the different pieces of the human body, and how each individual one works and how they fit together with the rest of them gives us like the human body that we have today. And so, by understanding each of the pieces, that gives you a greater understanding of the human being as a whole. If you are a chemist, then your pieces are the chemical elements. And the way those chemical elements combine tells you different properties of the molecules and stuff that they are making. If you're a geneticist, then the pieces that you're talking about are DNA, or the genes in your DNA. And for us as particle physicists, the pieces that we're talking about are just the most fundamental, the smallest, tiniest pieces that you get that make up everything in the universe.
Yeah, so underneath all the chemicals, the genes, the organisms, and all of those things, the particles are right at the bottom of all of that.
Yeah, exactly. They're the smallest. They are level 0.
I keep thinking of Lego building blocks, and they're like the ones that are just the one little kind of nubbin.
Right, exactly. So the thing is, we don't only have even your fundamental Lego set, right? Your set is not just the Lego blocks of the one. Yeah. There's a few different ones, right? So you have ones of different colors, and then you have ones that are 2s and 4s, which can correspond to particles that are heavier or lighter, and then also you have a set of rules that tell you how you are allowed to put your little Lego blocks together. Mm-hmm. And that set of rules in particle physics is what we call the standard model of particle physics. It's a pretty boring name for something that's really, really important. It's basically the set of rules that allows our fundamental building blocks, our little Lego particles, to fit together to give us the universe that we see today. Not any other different type of universe, but this particular universe.
And so then can you give us some examples of particles that we might know of?
Sure. So probably the one that everybody is most familiar with is the photon. So the photon is the particle of light. In particle physics, we think of everything as particles because that's why we call it particle physics. But most people are also are familiar with the concept of light being a wave. So in quantum mechanics, it's kind of funny, but things are both particles and waves at the same time, which is really cool and also really weird at the same time. And it's kind of one of the things that makes this a really, really fascinating thing to study. But anyway, in particle physics, we just think of everything as particles. So our photon is the particle of light. It's right now when you are looking at your screen or looking outside or whatever, photons of light are coming into your eye and hitting at the back of your eye on your retina and sending a little electric signal to your brain, which your brain is interpreting as seeing a picture. So photons are the ones that we're most familiar with. I'm sure people have heard of electrons too. Electrons are these little negatively charged particles that move around that create electricity. I'm sure people have heard of protons too. So an atom, for example, is a proton and maybe a neutron or two with an electron orbiting around it. So hydrogen, the most fundamental element, is one proton, one electron. But a proton is actually not a fundamental particle. We've discovered that a proton is made up of smaller particles called quarks.
Ah, wow.
So there are 6 different flavors of quark, but they combine in different ways to make protons and neutrons and other things like protons and neutrons. So quarks are the fundamental particles. Then you have the electron. And you also have 2 cousins of the electron that's slightly heavier. Nobody really knows why we have these 2 extra guys, but the universe has given us like a set of 3 things in all cases. That's a question that we're still trying to answer. And then as well, so we've got the quarks, we've got the electron and its family, and then we've got the neutrinos as well. So neutrinos are tiny little particles. They're very, very light. They don't interact much at all. Billions of them are coming out of the sun. They're being produced in the center of the sun as the sun burns its fuel and produces energy. These billions of neutrinos are streaming through your body as we speak, not doing anything, no problem. They're so tiny, they're so small. They're also really crazy, weird as well, which we can talk about later. So those are all the matter particles. These are the particles that make up stuff. That's the quarks and the electron and the muon and tau. Those are the electron friends, and then the neutrinos. Now, a photon that we mentioned first, a photon is not a matter particle. It's actually a force particle. The photon carries what we call the electromagnetic force. Or in other words, everyone knows that if you take two like charges and you push them together, then they repel. In particle physics, the way we think about this is that when you take two like charges, like for example, two electrons, and you push them together, those electrons exchange photons between each other, which pushes them apart. Mm-hmm. So the photon is carrying this electromagnetic force. I'm not sure if I'm explaining that very well.
No, I think so. I think it makes sense. I think I'm a bit stuck on the idea. Well, not stuck, but it's kind of blown my mind to think that photons are a force. So does that mean light is a force?
Yes, it does. Light is just the electromagnetic force. Exactly. Maybe, yeah. So it's just weird to think about it because we're so used to thinking about force as this spooky action at a distance thing. Mm-hmm. When in actual fact, it's really what you can imagine is just, things exchanging particles in between each other.
That's funny. That makes a lot of sense to me because I quite often think of the universe and everything in it it's almost like the Matrix, almost like everything. Because when you look at air, like the room that I'm in right now, like I'm standing in it and I feel like a solid body, but I'm in the air, and air feels like nothing. But the air is particles as well, isn't it? So I almost think of like this whole room is just like a big box full of particles all squashed in together.
Yep. There's just some areas that are a little bit more squashed of particles than others. Okay. Like you and me are just, more squished particles together. Although we are still so much empty space. The really interesting thing about even just an atom is how much empty space is actually inside one atom. Like if you take a hydrogen atom, which is one proton and one neutron, and you blew that proton up so that it was the size of a football, and you put this football in the center of the football stadium, the electrons, the closest electron would be way, way up in the top bleachers, the furthest away stand. And everything in between is empty space. So if you took all the atoms in every human being on the planet and you squished the electrons down right next to the protons, so you took away all the empty space in all the atoms in all the human beings on the planet, guess how much space we would fill? Take a guess.
I'm thinking something ridiculous, like something the size of a pea or something like that.
Not too bad. All the human beings on a planet would fit into a teaspoon.
No.
I promise.
I completely trust what you're saying. That's just.
But amazing. It's ridiculous. It's it's a little bit of comfort. Like once after the Christmas period when we've eaten all the chocolates and stuff. Like I'm mostly empty space, so.
Excellent.
Right. But so we were just talking about forces. So in particle physics, we've got this electromagnetic force, which is carried by photons. And then we talk about two other forces, the strong nuclear force and the weak nuclear force. So the strong nuclear force is the force that holds the quarks together to make protons and neutrons. And it also helps hold the protons and neutrons together inside the nucleus. And then the weak nuclear force, this is the force that's actually responsible for radioactive decay. So, for example, when you have like uranium that decays into something else, also in the center of the sun as part of the fusion process, this also happens. So, and these are also, these two forces are also carried by particles. But the one force that we don't have, that we don't actually think about in particle physics, is gravity. And that's because even though it's, the most obvious one, first of all, it's really, 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 really weak on these tiny, tiny scales because the masses of these particles are so very small, if not zero. But also, we haven't really figured out the math to put gravity and quantum mechanics together and get something that is not rubbish. So we haven't really figured out how to put gravity and everything together. So we don't talk about gravity when we're talking about particle physics, but of course gravity is definitely a force that is in the universe. But that also tells us maybe something a little bit interesting about gravity, that it's not exactly the same mechanism, or it's not really the same sort of force as the other forces are, because we can't use the same type of maths to describe it.
Yeah, and is that partly why physics seems to be a little bit separated between the particle physics at that very tiny level, and then I don't know what you call the other aspect of it.
Astro and cosmology.
Yeah, and
if we're talking about the electromagnetic force, right? You've got positive charges and you've got negative charges, and on the whole, the universe is pretty neutral, right? You've got the same number of positive and negative charges, so on the whole, everything sort of cancels out. Gravity, the charge of gravity is mass, right? In fact, for those of you who've done like physics at high school, if you write down the formula for the Coulomb Force, it's F. The force is proportional to Q1, Q2 over R squared. So the two charges divided by the distance, the square of the distance between them. And that is exactly the same as you would write for gravity, except in place of charge, you've just got mass. So it's M1, M2 over R squared. So gravitational charge is mass, but you don't get negative masses. You only have things that have mass or no mass. So on the whole, over the universe, mass just gets more and more and more and more, which is why gravity, even though it's such a small force, such a weak force, when you're talking about individual particles, when you sum that up over stars and planets and galaxies and everything and superclusters, then you have a lot of gravity to talk about, and that's where it gets really important.
Yeah, so that explains why as people we don't end up getting caught in orbits around other people, but planets will get caught in orbits around other people.
Exactly.
Other people, around other planets.
Exactly.
Okay. You actually, now you were saying, kind of study neutrinos in particular, so how did neutrinos fit into all of this?
Neutrinos are really interesting little guys. So neutrinos are produced, for example, during radioactive decay process. And you've got, so we have the electron and its two friends, the muon and the tau. And for each of those, then we have a neutrino that goes along with it. So we have the electron flavor neutrino, and we have the muon flavor neutrino, and we have the tau flavor neutrino.
And muon and tau are just other kinds of particles?
Yeah, exactly. They're particles. So the muon and the tau is exactly the same as the electron, except each is a little bit heavier. So you have the electron, and then you have the muon, which is a heavy electron, and then you have the tau, which is a heavy muon. Yeah, so neutrinos are really interesting because the universe is full of them, but it's very difficult to detect them because they'll go through light years of lead without stopping. But the thing about neutrinos is they do this thing called oscillating. So most of the other particles if you start off with an electron and you shoot an electron across the universe and you go to the other side of the universe and you collect that electron when it gets there, it's going to still be an electron. Mm-hmm. And the same thing for a photon or for an up quark or whatever. Those guys are going to be the same particle they were when they left. But neutrinos don't do that. If I take an electron neutrino and I shoot an electron neutrino and I go, I don't know, even a few hundred kilometers down the line, and I catch this electron neutrino, there's a high likelihood that that is not going to be an electron neutrino anymore, but it's going to be a muon neutrino or even a tau neutrino. So we call it neutrino oscillations because these flavors in the neutrino actually oscillate. They change into each other and then back again. So as a neutrino travels, it'll go from an electron neutrino, then it'll suddenly be a muon neutrino, and then it'll be a tau neutrino. And then down the ways again, it'll be back to being an electron neutrino. And then the whole process keeps going on and on and on forever. And this is really fascinating.
So as the neutrino moves from one side of the universe to the other or wherever it's going, does it go through a set order of how it changes between the types of neutrino?
Yes. So what we actually talk about when we talk about neutrino oscillations is we talk about the probability of finding a neutrino as a different type of neutrino. So if we start off with an electron neutrino, for example, then we will say that at this distance down the line and with this energy, then we will have a 90% probability of finding it as a muon neutrino. And then so much further on, we will have a 30% probability of finding a muon neutrino and a 60% probability of finding it as a tau neutrino. So yeah, this is the way that it oscillates.
And do you, I guess maybe this is something you're still working on, but trying to understand why that's happening?
So we understand why it's happening. And so the reason why it's happening is because what we call the neutrinos, what we call an electron neutrino, a muon neutrino, and a tau neutrino, those are not like the fundamental neutrino state. Mm-hmm. So think of it like this, okay? So those are not the fundamental neutrino states. The fundamental neutrino states are the mass states. So we call it mass 1 neutrino, mass 2 neutrino, and mass 3 neutrino. And each of these has a different mass. Now, the electron neutrino is a combination of those three mass states. The muon neutrino is a different combination of those three mass states. And the tau neutrino is a third combination of those three mass states. So you can imagine it as, because you're the Curiosity Cake podcast, so let's imagine neutrinos as cake because everything is cake. So imagine that you have a cake of 3 layers, and your electron neutrino cake, the 3 layers are, there's a very fat layer, and then a medium layer, and then a thin layer. Those are like the 3 layers. Then your muon neutrino cake will also be made of 3 layers, but it'll have different sizes, different proportions of those layers to make up the cake. And your tau neutrino will be a different 3-layer combination. Now, what happens as neutrinos travel is these layers change. So the layers travel at different speeds. Through as a neutrino is traveling, the layers are obviously traveling, but the layers are traveling at different speeds. And that's why as the layers travel, you start off with 3 layers in a particular combination, but as the layers travel, one layer maybe moves faster than the other, so it takes up more space, and the other layer takes up less space. So a little ways down the line, you've now changed your configuration of layers, and therefore you've changed from an electron neutrino to a muon neutrino or whatever. So we understand why this is happening, but one of the really interesting questions is whether or not this happens the same way. So whether or not this transformation, this oscillation happens the same for neutrinos as it does for antineutrinos.
Oh, no, what are anti-neutrinos?
So everything in the universe, so we've been talking about particles, but for every particle there is also an antiparticle. And an antiparticle is exactly the same particle, but with opposite charge. So for an electron, you have an anti-electron, which is called a positron. So a positron it looks and feels and smells and is exactly like an electron, except it's just positively charged instead of negatively charged. Mm-hmm. And for every particle, you have an antiparticle. It's very normal stuff. We create these antiparticles all the time in our collisions in the LHC. You get antimatter forming in cosmic rays coming in from that upper atmosphere, all this sort of stuff. So antimatter is very normal stuff. And so, if you've got neutrinos, then we've also got antineutrinos. So the question, one of the big questions that scientists are trying to answer in the next decade is, if I take a muon neutrino and I shoot my muon neutrino cake off and I watch how those layers change, and then I take an antineutrino cake and I shoot my antineutrino cake off and I watch how the antineutrino cake layers change, do those layers change in the same way, or do they change differently? Mm-hmm. And if they change differently, that will be super exciting because that will tell us something very fundamental about the way that the universe works. And it'll indicate that there's this difference, there's a fundamental difference between neutrinos and antineutrinos that might even be able to explain one of the as yet unsolved mysteries of science, which is why the universe even exists at all. Yeah, I mean, you would think we would know the answer to that by now. We actually don't even really know why we're here, and not even like at a philosophical level, but just why is there a universe?
Yeah,
because
I think I've seen there's a YouTube video where someone's asking the question, why is there something rather than nothing?
Exactly. We've got when the Big Bang happened, right, there was nothing before, and then the Big Bang happened and energy and matter were created in that moment. And there's this thing called the conservation law, right, which means that if you have nothing overall before, then you need to have nothing overall after the Big Bang. So like I said, every matter and antimatter have opposite charges. So when the Big Bang happened, you had an equal number of particles and antiparticles being produced. So for every electron that was produced in the Big Bang, you also had an anti-electron. For every neutrino, you had an antineutrino. For every quark, you had an anti-quark being produced. So that's very great because that balances out. That balances the equation before and after. Awesome. So we assume that there was an equal number of matter and antimatter produced at the Big Bang. Now, when matter and antimatter come into contact, it annihilates in a burst of energy. So for every electron that bumped into an anti-electron or positron after the Big Bang, you would have had an annihilation, boom, created some energy. So if we started off with an equal number of matter and antimatter, and then it would have annihilated and annihilated and annihilated itself, why were we left over with enough of a handful of matter to create the stars and the galaxies and the planets and everything that we see in the universe today?
And am I right in thinking then that the matter in the universe actually makes up a very small proportion of the universe itself, and the rest it's mostly antimatter? Is that right? No. You can
Actually,
say no.
no. Well, no. So we live in a universe that's made of matter.
Mm-hmm.
Everything that we see, you are matter, you and me are matter. Yes, we can create little bits of antimatter inside the LHC, but then then it as soon as it gets in contact with an air molecule or whatever, some normal matter, it annihilates. So that's fine. But yeah, we are made of matter. All the stars in the galaxies that we know of, we assume are also matter. So everything is matter. But I think maybe what you're thinking of is if we add all of that stuff up together in the entire universe, then that makes up only 5% of the entire universe. And even including the antimatter, that's still only 5% of the universe. And the rest of the stuff is what we call it dark matter and dark energy. So we have a name for it, but we really have no idea what it is. Most, like 95% of the universe is stuff that we don't even know.
I'm really wondering now about how our understanding of these particles now helps us understand like what happened in the past. So we're talking about the Big Bang, which obviously happened a long time ago. Is it a similar kind of process to like the evolution of like living creatures, where humans came along at the end of or towards the end of the process that we understand as evolution, and before that all started with like single-celled organisms, things like that. On the particle level, is there a similar kind of evolution process like that, or all the particles that we know they exist now, they all existed at the Big Bang?
So you're right in both ways. All the particles that exist now, all the fundamental particles that exist now also existed right after the Big Bang. The difference is in how they're able to fit together. Because to form a hydrogen atom, all right, that's one proton with one electron going around it. Now, it actually took the universe almost 400,000 years before it could get to the point to create, 300,000 years, before it could get to the point where it could make hydrogen atoms. And that was because the universe was so hot. What we started off with were quarks and photons and electrons just all flying around. And the universe was so hot, all of these particles had so much energy that they weren't being caught in orbits and being caught, to form like groups with each other. So like imagine you are in a crowded room and everyone is just running around. You're not, if everyone's running around a lot, nobody's going to settle down and start talking to one another. But as the energy of the room goes down, as people start walking slower and slower, then people will start coming together in groups of 2 or 3 or whatever and start forming little groups. It's the same thing that happened with the particles. Right after the Big Bang, the universe was so hot, these quarks and everything were flying around. After, I don't know, a few like minutes or something, about 3 minutes, within the first 3 minutes, the quarks, the universe had cooled down enough so that the quarks could group together to form protons and neutrons. And then after about 3 minutes, even some of the protons and neutrons could get together to form helium nuclei. But it still took about 300,000 years before the universe cooled down enough for those nuclei to capture electrons to form neutral atoms. So all the pieces were the same, but the way that they were being put together has evolved over time as the universe has expanded and cooled down.
And I'm wondering how can we understand, like you're talking about like 3 minutes from the Big Bang, like how can we really understand what's happening at that time?
Well, it's kind of weird. I mean, so this is why we build big particle accelerators like the LHC and the Tevatron before that, and RIC as well, which is one in the US, because one of the things that happens when we smash particles together inside these machines is that you're going back to, for just for a fraction of a second, you're going back to the energy and the particle density and stuff that it was that things were like at the beginning of the universe. So by doing these experiments, we can recreate the conditions of what things were like in these first couple minutes after the Big Bang. And then we can study, what happens in these moments, and then that tells us about what was happening immediately after the Big Bang. It's kind of like a different kind of telescope, right? You grab a telescope, you point it in the sky, you look far away. The further away you look, you look back in time, you see the way the galaxies were, thousands of years ago, or whatever. This is just a different type of telescope that we're using. It's just we're using particles to look at what the universe was like, 13 billion years ago.
So talking about the past, maybe let's talk about the future a bit. What do you see as being the big questions that we hope to resolve in particle physics, like in the next 10 years or in the next, by the end of the century?
Oh, that's awesome. Wow. So let's see. One of these big questions is, why do we even have a universe, right? This is this asymmetry between matter and antimatter. So there are a bunch of neutrino experiments trying to see if there is a difference between the way neutrinos and antineutrinos oscillate. If that is the case, it's possible that we will know the answer to that, in the next 10 years or so. Wow. Yeah. So that would be really cool. But it's not a guarantee. Like we're also studying it, so we don't know if that's actually going to answer the question. If there's no difference between neutrinos and antineutrinos, then that doesn't answer the asymmetry question.
Back to the drawing board.
Yeah, well, so then people are looking for answers to the asymmetry problem in other places as well, right? But if we're talking about the neutrino and the neutrino antineutrino oscillation, then maybe in the next 10 or so years we will have an answer. So that's the one I'm really hoping for, because I think that would be really, really awesome. So yeah, that my bets are hedged on that. Okay. What else? So then there's this question of, what is the other 95% of the universe? And this is more tricky, right? So this is split up into two parts. So we've got dark matter and we've got dark energy. Now dark matter is stuff. It's probably particles, but just particles that we haven't discovered yet. Mm-hmm. And this is it's almost a luck thing. We've been hunting for these potential dark matter particles at the LHC now. We haven't discovered any of them yet. That could mean that could mean three things. That could mean there's no such thing as a dark matter particle, and we've got it all wrong. It could mean that there is such a thing as dark matter particles, but we just haven't got the energy to create them at the LHC. Mm-hmm. And it could also mean that there is such a thing as dark matter particles. We do have the energy to create them at the LHC, but they get created so rarely that we haven't done enough collisions at the LHC yet to have seen them. Mm-hmm. So the first one, that one's a bit of a useless point. So let's focus on these other two. I mean, if they're not there, then they're not there. But you'll never know until you've crossed out all possible avenues, right? Mm-hmm. So we've got to do that. So the other two, if they're at the LHC, but we just haven't taken enough data to discover them yet, this is why we're keeping the LHC running for the next 16 years or whatever, and why we continue to take data with the LHC even after we discovered the Higgs. We discovered the Higgs, that was great, but we're keeping on to take data to collect up as much stuff so that maybe we could see these rare type of events if that is the way that the universe works. If that's not the way that the universe works, and in fact we just don't have enough energy, well, then the next thing is to build a bigger machine and to get a bigger machine with more energy and smash the particles together there, and maybe hopefully we will have enough energy at this bigger machine to create these particles. And if not, that's also cool, because even then we'll learn something really, really interesting about the way that our universe works at these different energy levels. So that's that. Those are so let's see, what were those questions we had? What's the deal with the matter-antimatter asymmetry and why are we even here? We have, what is the other 95% of the universe? Okay, the dark matter part. The dark energy stuff, we leave that to the cosmologists. That's their baby. We'll focus on the dark matter side of things, because these are particles that we can deal with. And then I guess the third really important question is, what really is the Higgs boson? Mm-hmm. Because we don't know it as well as we can. So another thing that's useful to do, the next big machine that we need to build, is a Higgs factory machine, where we can just focus on producing loads and loads of Higgs bosons, and then we can study these Higgs bosons really, really closely and learn everything that we need to know about these Higgs bosons. How do they work? How do they fit together? How do they interact with other particles, and how do they interact with themselves? So these are the next, I think those are the three next important steps that will be the future of particle physics. So the first one is, like I said, about maybe 10 years. We may have an answer if we're lucky there. Mm-hmm. Building the new machines is going to take a bit longer, because it took 20 years to build the LHC and another 20 years to run it or so. We're looking at building much bigger machines, which is going to take a lot more time, require a lot more commitment from governments and funding agencies and people. But like going back to what we said at the beginning, it's an exploration. It's like climbing Mount Everest, right? We do it because we can, and because it's exciting to do, and because we don't only learn about the universe along the way, we also, I think, learn quite a lot about ourselves.
Well, Claire, I think that's a really good place to end then, looking into the future and kind of hoping various governments will throw some money your way to do all of that work. And maybe I can talk to you again in 10 years and see if we've come up with that answer.
That would be awesome.
That would be great.
That would be awesome. I hope to have some excellent news for you by then.
Me too. I'll be keeping a close eye on it. So Claire, awesome. How can we find out more about your work?
You can go to the CERN website, which is home.cern. You can, so that, they've got some great links and everything there, great public page. You can learn everything there is to know about CERN physics. You can also go to the Fermilab website. So just Google Fermilab, Fermilab. And yeah, that'll tell you about the lab that is in the US, which is building this, next big neutrino experiment that is hopefully going to answer that first question. And then, of course, you can follow me on Twitter. My handle is Claire_Lee. Very easy. That's mostly and then, if whatever your favorite social media platform is, whether it's Twitter or Instagram or Facebook or whatever, all of these labs, CERN, Fermilab, the experiments themselves, they all have very good presence on social media as well. So this is just, especially in these times where we can't necessarily travel and go visit places, I think following these social media accounts for the labs and stuff are a really, really cool way of keeping up with the latest stuff that's going on.
Brilliant. Everyone check out those. I'll have links to some of those in the show notes. Claire, that's been an absolute pleasure. Thanks very much for your time and for your very in-depth knowledge of what the universe is made of.
Thank you so much, Lee. It was fantastic to talk to you. Thank you for the excellent questions. You had me thinking on my toes there. So that was very cool.
Excellent. If I could make a particle physicist think, I've probably had quite a productive day then.
I think you deserve a glass of wine now.
Thank you. That's awesome. Thanks, Claire. I hope you've enjoyed listening to this episode. Remember to rate and review the show on your podcast app and spread the word. And get in touch on Twitter or through the website and let me know what topics you'd like to hear in the future. Bye for now.